if we look into the internal architecture of 8085, so if we have a look at the block diagram level view of this 8085. Now, you see that there are some special registers like this accumulator is a special register, then this temporary register. So, this is another special register, and this flag register. So, this is another special register. So, they are actually in conjunction with this arithmetic logic unit. So, as we have seen that any processor, it will have an arithmetic logic unit, it will have some register file consisting of a set of registers and some controller. Okay. So, in that light, so if we just try to look into the details of this 8085 internals, so you will see that this ALU part, so if you blow it up a bit, then you will find that the ALU is consisting of not only the ALU, but this special register, A register, temporary register, and there is a set of flag register. There is a flag register which consists of a set of flip flops. There is A register is 8-bit wide, temporary register is also 8-bit wide, and the flag is 5-bit wide. And this ALU, it does operations in 8-bit in terms of 8 bits. And there is an internal data bus which is 8-bit wide. So, all the data that are flowing through the internally through the processor, so they are 8-bit at a time. Now, let us look at it from the outside, like the way the instruction comes to the processor, how does it continue. Okay. So, when the instruction comes, so this is the instruction will come through this line, this AD7 to AD0. When this part is we assume that it is configured as data bus. So, the outside world, the first instruction has arrived here, then this instruction will go through this line. So, it will come to the instruction register. So, the instruction reaches the instruction register, and then this instruction register, the opcode part of the instruction, so it is decoded. Okay. So, instruction decoder and machine cycle encoding. So, this particular module will decode the meaning of the instruction, and it will also tell what are the operations that it has to do. So, accordingly it will instruct the timing and control logic, and it will, that is, this timing and control logic will get the instruction opcode from this instruction decoder. It will generate the clock signal, it will get the clock signal, and it will have this clock out, it will have the clock signal from the outside world. And so, it has got many other lines which are acting as input or output, like this clock out signal. So, this is basically generally it is the clock out value. So, whatever clock signal is coming in, so that is generated as clock out. Then this read bar line, so read bar line is given as control output. So, write bar line is also given as control output. The arrow is missing here, but the arrow will be outside. In fact, so wherever the arrows are missing, I think this will be the outward direction. Then this so let us look into the signals that are coming into this timing and control module. So, clock is one signal, and clock generator, because there are that crystal will be there. So, crystal will be connected between these two pins, the clock generator pin. Then this ready signal. So, ready is a special signal. So, we will see it in detail later, but what it essentially does is that if the memory chip with which you are connecting the processor, if that memory chip is slow compared to the processor. So, processor, after it has put the address onto the address line, so it will expect the data to be available after some time. If the memory is not able to give the data within that time, then it should tell the processor that I need the address for some more time. So, in that case, it will put this ready signal high, telling that the memory is not yet ready. So, the data is not yet available. So, that way this ready comes as input to this timing and control module. Then this then the next input line we have is the hold line. So, hold line will be it is important with respect to special type of operation which are known as direct memory access or DMA. So, in DMA, what happens is that there may be multiple processors connected to the same bus, and they are talking to the same memory. So, when that is the case, the multiple processors are masters of the same bus. So, there will be contention, like which processor will be accessing the bus next. or so the policy is that whenever a processor wants to use a bus, so it will send a hold signal, so that the other processor will be releasing the bus, and it will send a hold acknowledgement telling that okay, I am not using the bus, so you can use it now. So, this hold and hold acknowledge, so these two pins are used in that purpose. So, we will discuss it in more detail when we go into this DMA data transfer type of operation. Then this reset in bar, so this is basically the reset pin. So, if the reset pin is pressed, then this reset in bar line will be activated, so that it will be reset and it will generate the reset out. Then it will generate the hold will generate hold out. Then this status line, so S0, S1 and IO M bar, so that will tell you the status, like as I have already said the which operation it is doing now, and whether IO operation or memory operation. And the ALE signal, so ALE signal, so this is an output, so this will be used to demultiplex the address and data bus values from the multiplexed address data bus. So, other than that, so we have got this general purpose registers like B register, C register, D, E, H and L. So, these registers, so they are all 8-bit registers. However, in some instructions, so you can use them as 16-bit register pair as well. So, in that case I have got register pair B, which consists of the registers B and C, making it a total of 16-bit. We have got register pair D, making it DE as a pair, and H, HL as a pair. So, these are all individually 8-bit register, but when you are taking two of them together makes a 16-bit register. Then there is stack pointer. So, stack pointer we will discuss later. So, this is a special purpose register which is a 16-bit register. Then there is program counter. So, program counter is actually just like in the architecture portion we have discussed. So, it will tell like what is the next instruction address to be accessed. So, if you reset this processor by putting a reset bar line high, what happens is that this program counter value becomes reset to 0. So, this value is reset to 0. So, as a result, this next time this the processor goes into the instruction fetch cycle, this 0 value will be put through this address buffer to the address bus. So, the memory as if the processor is now trying to access from memory location 0. So, if your system initialization routine starts from address 0, so then the system will get initialized. So, that way this is the special thing. So, when this reset in bar pin is activated, this program counter value becomes 0. So, that way it goes on. So, then there is a incrementer decrementer address latch. So, this is basically for incrementing decrementing the address part. Some additional circuitry will be required, some latches will be required. So, that will constitute another 16-bit. Other than these, so we have got this serial IO control, so which will be controlling the SID and SOD lines, serial input data and serial output data, these two lines. There are interrupt control, so that will model that will handle the interrupts. So, if you want to tell the processor from the outside that something extra has happened, something special has happened, and that has to be taken care of. For example, if this 8085 microprocessor is used for controlling the operation of a plant, then if there is a fire detected, so some smoke detector detects some smoke, then it can send interrupt to the processor telling that okay, some abnormal situation has been detected, and this interrupt comes to the processor. Then we will see later that whatever the processor was doing, that will get suspended for the time being, and it will go into execution of the corresponding interrupt service routine for servicing that extraordinary situation. Okay. So, these are the internals of 8085. So, this is the document released by the designers, the Intel people, and as a user of the system, so we get to know that okay, these are the special registers that are these are the registers that are there. So, which register is accessible in which instruction and how they can be used, etc. That will be documented in the remaining part of this discussion. So, if we summarize, so this microprocessor consists of control unit, ALU, registers, interrupts and internal data bus. So, out of that this control unit will control the total operation of the microprocessor. ALU will perform data processing function. So, whatever arithmetic logic operations are necessary, so that will be done by the ALU. Registers, they will do they will provide the storage internal to the CPU, and so actually this is very interesting, because so if you want to access a particular data, or if you want to do an operation very fast, then if the operands are in memory, then while doing the operation I should bring the operands from the memory to the ALU for doing the operation. But if they are in the CPU registers, then that is internal to the chip. So, no external access is necessary. As a result, the operation will be much faster. So, if you are really looking for faster execution, then you should put the operands of these instructions into the register. Of course, that may not be possible because registers are limited in number. So, we have got only say B, C, D, E and H, L. So, only these 6 registers are available in the inside the CPU. So, only the most important variables in the program, they can be put into those registers, and the remaining ones will be in the memory and their operation will be slow, but this essential, the critical ones, so they can be made faster. So, these registers, they provide storage internal to the CPU. Then interrupts are there, and for interrupting the system and telling that something special has happened and that to take care of that situation. And there is internal data bus. So, that will be connecting the modules internal to the processor. So, the ALU, so in addition to arithmetic and logic circuits, the ALU includes the accumulator, which is part of every arithmetic and logic operation. I would like to highlight this point, that it is part of every logic of arithmetic and logic operation. So, for any operation, this ALU, any ALU operation, this accumulator is taken as one of the operand or the first operand, and the result is also stored in the accumulator. So, it is the source operand, the first operand, and as well as the destination of these operations. So, also apart from this accumulator, so there is a temporary register that holds data temporarily during execution of the instruction, and this temporary register is not accessible by the programmer. So, programmer does not have any access to this temporary register. So, if we just go back and look into this diagram, like this ALU, when it is doing the operation, so it needs the value to be available at its input, and these values available at the input, they should be stable values. Okay, they should not be floating around this bus. Like if I am trying to add the content of A register with B register, then the B register value should be available here in a steady fashion. So, what the system will do, it will transfer this B register value to this temporary register, and then it will give the add signal to the ALU. As a result, the values will be added and the result will be available onto the bus, which will be stored in the accumulator. Or if it is trying to add A with some memory location content, then the memory location content will come to this data buffer through this bus. So, it will come to the temporary register, and this timing and control module, so it will generate the appropriate control signals for doing that. So, the value will be loaded into this temporary register, and then the value will be added using this ALU and stored back into the accumulator. So, this temporary register is not accessible by the programmer, because programmer is not supposed to know. In fact, what is the structure of this temporary register, it is not revealed by the Intel people. So, it is just said that something like that is there inside. So, whether it is an 8-bit register or something more than that, so that is also not clearly told. So, as far as the users are concerned, so users will see these registers, the accumulator, flags B, C, D, E, H, L. So, these pairs. So, out of these B, C, D, E, H, L. So, they are called general purpose register. So, the general purpose register means they are normally used for this ALU operation. Okay. So, all of them are 8-bit register and can be used singly. So, you can use this BC these registers, one register as an 8-bit register, or you can use it as 16-bit pair like BCD HL, 16-bit pair also you can use, and H and L they can be used as data pointer. So, this is another very interesting thing, like say many times what happens is that we need to implement a pointer in our program. So, for pointer what is required is that the operand that we have in the instruction, that is not the actual operand, but that is an address of the operand. So, you have to access the memory location pointed to by that particular operand to get the actual value. So, this HL pair when it is used as this pointer, so this can be used to hold some memory address, and what the processor will do, it will not use HL register pair value as the operand, but it will be using the corresponding memory location as the operand. So, this helps in implementing the pointers in high level languages. Apart from that, there are special purpose register. So, one such special purpose register is the accumulator. So, accumulator is an 8-bit register, and it is normally it is storing the first operand as well as the result of any operation. Another special register is the flag register. Now, while doing this arithmetic logic operation, various exceptional situations can occur. For example, when I am storing a number, so the number may be positive or negative. So, when I am storing a number in the accumulator, if the accumulator content is negative, then there may be some decision that I need to take based on that situation. So, we need to know what is the value of this operation that has been done, the last operation, whatever operation has been done, what is the result of that, the type of the result. So, if the result after doing the operation is say negative, then this particular bit D7 of the special register flag will be set to 1, telling that the result was negative, and the result, if the result is positive, then this D7 will be 0. The last operation, maybe it has resulted in the value being totally 0. Maybe we have subtracted two same values, and as a result the result has become 0. So, in that case this D6 bit will be set to 1, telling that the 0 flag, the result has been 0. So, this particular bit will become 1, telling that the result is 0, otherwise the Z bit will be equal to 0. Then this D5 is not used. Similarly, this D3, D5, D3 and D1, these 3 bits are not used by the processor designers. So, we have got a carry bit, which is the CY, the carry bit. So, when we are doing some addition or subtraction operation by the ALU, so it can generate a carry. If the carry is generated, then this D0 bit will be equal to 1, telling that a carry has been generated, otherwise this bit will be 0. Then this bit D2 is the parity bit. So, telling that whether the result that we have is having an even number of ones or not. If it is not, then this P bit will be 1. If it is yes, then this P bit will be 0. Then we have got another bit D4, which is the auxiliary carry, telling that it is after doing the addition. So, after 4 bit whether there was a carry generated or not. So, this will be detailed in the next few slides. So, first one is the sign flag, as I was telling that it is used for indicating the sign of the data in the accumulator. It may be negative, it may be positive. So, if it is negative, then it is 0, it is 1, and if it is positive, the bit is 0. We have got 0 flag. If the result obtained after an operation is 0, then the 0 flag will be set. Is set following the increment decrement operation of that register. So, if it is some register operation is done, increment register, decrement register, or some addition subtraction, a 0 flag may be set. So, carry flag will be set if there is a carry or borrow from the arithmetic operation. So, for subtraction it is a borrow, for addition it is a carry. So, if something is carry or borrow bit is generated, then this carry flag will be set. Then there is auxiliary carry. So, auxiliary carry is set if the carry is from bit 3 there is a carry out. So, from bit 3, so if the result is 8-bit result. So, from if bit number 3 to bit number 4, if there was a carry generated, then this auxiliary carry will be set. So, this is many times this is necessary, particularly when we are doing operation with some binary coded decimal format, then this auxiliary carry bit is necessary. So, it is kept for that purpose. And this parity flag, so it is set if parity is even and is cleared if parity is odd. So, parity is even means if the number of ones in it in the accumulator is 1, then it is set to 1, and if it is odd, then it is set to 0. Now, apart from these general purpose registers, like we have got special registers like accumulator and flag, the other register that we have is the program counter. So, this is a very important register because this is used to control the sequencing of execution of instruction, like which instruction will be executed next by the processor is decided solely by the content of this register. So, it holds because it holds the address of the next instruction. So, since it is holding the address, and address is 64 the address can be up to 64 kilobyte size. So, it can be in the 64 kilobyte range. So, it has to be 16 bit wide. So, that way I can have this program counter register. So, it will be doing sequencing of operation. So, I hope you understand that if you are trying to jump from one location to another. Okay. So, suppose I am at present executing instruction at memory location 1000, and the next instruction I want to execute has to be from location 3000. Then what I need to do essentially is that this program counter value somehow it should be loaded with the value 3000. Okay. So, that is the thing to be done. So, this is taken care. So, this is done. This is the responsibility of the program counter. Another very interesting register that is there is the stack pointer. So, this is also a 16 bit register, and it points to a particular position in the memory, and this memory this register points to is called a special area called stack. So, this is an area of memory to hold the data that will be retrieved soon, and this is goes in a last in first out fashion. So, we will come back to this stack later. For the time being, we just understand that the stack pointer is another 16 bit register that points to a special portion of memory called stack. Okay. So, we will come to this stack pointer later. There are some other non programmable registers. One is the instruction register and decoder. So, the instruction which comes from the outside world by the processor puts the address of next instruction onto the address bus, and the memory responds with the next instruction. So, next instruction when it comes to the data bus buffer, so it is directed towards the instruction register. So, the instruction is stored in the instruction register after being fetched by the processor, and the decoder will decode the instruction in the instruction register. So, instruction register's output will go to a decoder, and the decoder will decode that instruction. And there are internal clock generator. So, internally it is 3.125 megahertz and externally it is 6.25 megahertz. So, the crystal that is connected is of 6.25 megahertz and internal clock that is generated is 3.125 megahertz. Looking at the address and data buses, the address bus has 8 signal lines A8 to A15 which are unidirectional, and the other 8 bits, so they are multiplexed, that is time shared with 8 bit data bus. So, these lines A0 to A7, so they are actually the lower order address bus. So, they are multiplexed with the data bus. So, data bus is 8 bit only. So, D0 to D7. So, it is multiplexed with that. So, the idea is that when this address bus value is necessary. So, data bus value is not necessary at that point, and if it is necessary we have to take care of that, but assuming that they are not used simultaneously. So, we can multiplex their use. So, that is the basic idea of multiplexing. When I have got 2 items multiplexed on a line, then 2 items are not used simultaneously. So, I can use that for one at a time. So, in a multiplexed fashion, but we will see that it is not always true, particularly for 8085 it is not that this address and data buses are not needed simultaneously, because while you are trying to read from memory, So, this you have the memory needs that the address be stable when it is putting the data onto the data bus, the address bus value should also be stable. So, it is not a true multiplexing in that sense, but as far as the processor is concerned, so it is multiplexing in the sense that the same set of lines are being used for address bus and data bus. So, during the execution of the instruction, so these lines carry the address bits during the early part, and then during the late part of execution carry the data bits. So, at the beginning they will carry the address bits, towards the end it will carry the data bits. In order to separate address from data, we can use a latch. We will see, that is what I was talking about, that this definition of early part and later part. So, that is a bit fuzzy. So, when this where is the boundary? So, that is not very clear. So, as a result, to be on the safe side as a designer, so what is required to do is externally we differentiate this address bus and data bus. We do a demultiplexing of this address bus and data bus, so that the operations are done properly. So, this brings us to the concept of demultiplexing the address and data bus. So, this higher order address bits of the address, they will remain on the bus. So, we have no problem with the lines A8 to A15. So, there is no problem with those lines, because they remain in the bus for 3 clock periods. So, we will see later that when 8085 is trying to access memory, so it needs 3 clock cycles starting from the point at which the address is put onto the address bus till the memory will put the data onto the data bus and the value comes to the processor. So, that takes 3 clock cycles. So, in that in the first clock cycle, this higher order address bus will have the higher order the address bits A0 to A8 to A15, and the lower order address bus, it will have the value A0 to A7, and this A8 to A15. So, that will be holding for all the 3 clock cycles, but this A0 to A7 they are held for only 1 clock period, and naturally you need to latch them externally or save them externally, so that they are not lost in the remaining 2 cycles. To make sure that we have got entire address for the full 3 clock cycles, so we need to use some external latch to save the value of this AD0 to 7 for carrying the address bits. So, this is done by means of the ALE signal. So, that is, so what is done at the clock cycle, at the first clock cycle, this address, this on the line AD0 to AD7, the address bits will be put, that is the bits A0 to A7 will be put, and this ALE signal is generated by the processor. So, externally we can use this ALE signal to latch these values A0 to A7 into some temporary register, and from there the temporary register, even when the ALE signal is taken off, the value remain latched there, and this temporary register, it remain latched in that register, and from there we can drive the address lines for the memory.